Mpirical provide compelling, interactive learning across a range of delivery options. Live on site, live online, or online anytime, we have a training course that is ideal for you. For a no-obligations chat about your training requirements, contact us at mpirical.com.
In this video, we're going to take a high-level look at the protocols which operate across the GSM Air interface, namely DTAP, the Direct Transfer Application part, Radio Resource, and also LAPDM, the Link Access Protocol on the DM channel. Finally, we'll see how this information is coded and interleaved as it's transmitted across the GSM Air interface. So to begin with then, let's just take a look at which protocols operate where in terms of our GSM architecture. And here we can see on the diagram the relationship between these key protocols. So to begin with then, let's turn our attention to DTAP, the Direct Transfer Application part. This is really a series of signaling messages which are sent between the mobile and the MSE server. These are specific messages then between one subscriber or one subscriber's phone and the core network. Here we can see it's using the services, however, of LAPDM and the GSM physical layer to pass that information first of all across the UM interface, and then as it leaves the BSC of the A interface towards our MSE server. So what type of messages then can we categorize as our DTAP, our Direct Transfer Application part? Well, the DTAP messages can be broken down into two groupings. These messages which deal with mobility management and those which deal with call control. Now, we're not going to go through all of the messages because there are many associated with DTAP, but we'll pick out one of those to see how it operates. So if we turn our attention then to the DTAP mobility management group of messages, we can see we can further subdivide them into messages associated with registration, security, connection management, and miscellaneous messages. So if we look at those dealing with registration, these are the DTAP messages sent from the mobile up to the core network and vice versa, associated with the phone registering or deregistering with the GSM network, including things like the IMSI detach indication, which will basically be sent by the mobile when it powers off. However, the one we're focusing on here will be our location updating request message. This is a message sent by the mobile up to the core network when it powers on and wishes to connect through to the GSM system. There are other reasons why we send a location updating request when we cross a location area boundary or when our periodic timer expires, but it's simply a cause value inside the message indicating the reason for sending it. But here we can see it's a direct message sent from the mobile which needs to terminate on the MSC server. Radio Resource, however, we can see only operates across the GSM Air interface between the mobile and the BSS. However, it contains really two types of message sets, those which are dedicated to a particular mobile, but also common signaling which need to be interpreted by multiple mobiles. Again, we can see here the signaling message using the services of LAPDM down onto the GSM physical layer, the radio frequency layer, the RF layer, before being transmitted across and back up to be processed on the far side. So, what are the radio resource messages? Well, once again, there are many radio resource messages which are used within GSM, but these can be broken down into a number of different groupings. Those dealing with channel establishment, setting up the radio connection across the air interface. We must stress the radio resource is all about setting up resources on the radio link, the air interface. In addition, we have messages dealing with ciphering, turning on encryption, etc., handovers, moving a mobile from one cell to another, etc., etc. So let us just focus then on the handover group of messages, and we can see that within that there are many sub-messages dealing with things like handover complete, handover commands, etc. But also we note the assignment messages. The assignment is all about allocating resources for a particular mobile. This may be on the same cell and necessarily may not be what we would traditionally associate with a handover. However, if we focus on the handover command message, again, this will be an example of a radio resource message specific to a mobile which has been sent from the network down towards the handset. Again, typically indicating the new frequencies, power levels, timing advance parameters that the mobile will need to use when it switches into the new cell. Other types of signalling messages associated with radio resource, which are possibly based on common signalling, will be things like the system information messages. These are the rules and regulations which are broadcast from every cell, basically ensuring that the mobiles know how to operate within that environment. Sitting below then DTAP and radio resource, the next protocol is referred to as LAPDM, Link Access Protocol on the DM channel, or the modified D channel. And here we can see that LAPDM is used to carry the DTAP and the RR messages. But in addition, LAPDM is also used to carry text messaging. And therefore we need to use this to multiplex between our SMS messages and our signalling. And we do this with inside the frame format of our LAPDM protocol is a parameter referred to as a SAPI, the Service Access Point Identifier. And this is simply coded as 0 to indicate that we are carrying signalling, be that DTAP or radio resource, or set to 3 to indicate that we are carrying an SMS message. This then will be processed once again on the GSM physical layer and transmitted across the air interface. In addition, though, to carrying out this multiplexing process, LAPDM is also capable of supporting acknowledge mode. This means that should we have any errors or missing information, we can call for a retransmission at this layer, rather than having to wait for the message to be decoded further up the protocol stack. That just leaves us then the concept of channel coding and interleaving. So again, if we extend that process now, we can see that if we wish to carry our speech information, we're not actually going to be using the services of either radio resource, DTAP, or LAPDM. Here we can see that the speech is carried directly onto our RF channel for transmission across the air interface. Hence the coding and the interleaving will take place down at the physical layer, at layer 1, our RF layer here. So what's actually taking place with regard to voice? Well, with regards to voice then, we need to take our voice information and we need to code it into a digital signal. And to do that, we use different types of codecs. The common one here we're going to see is referred to as EFR, the enhanced full rate. And this takes the voice sample and codes it at a rate of 12.2 kilobits per second, a digitized version of voice. In addition, however, there are other codecs which can be used. And another common one we find now in GSM is referred to as AMR, adaptive multirate. And as the name would suggest, adaptive multirate has a number of different rates, ranging from 12.2 kilobits per second through to 4.75 kilobits per second. Now, the reason we have these different rates is not to enable us to carry more traffic. It simply allows us to add more convolutional encoding or more protection. One of the key aspects with sending voice across the GSM air interface is we need to ensure that we can correct for any mistakes. As this is a real-time application, we do not have time to call for retransmission. Again, we need to be able to correct for the mistake and continue the stream of voice through the system. Therefore, in the case of AMR, by applying more protection, by using a lower rate of codec, it means that we can operate in more hostile radio environments. However, as a result of sending either our EFR or our AMR coded voice down through our convolutional encoding process, the net result will be our encoded voice at a channel rate of 22.8 kilobits per second. This is for full rate operation. This results or manifests itself as 456 bits every 20 milliseconds. The 20 milliseconds is our sample size for voice. So what do we do with these 456 bits of information? Well, then we will spread them out or interleave them across a number of bursts. And in the case of speech, we spread them across 8 bursts, which means should we lose a burst due to a spike of interference across the radio link, we will only be losing 12.5% of our voice. And our convolutional encoding process is capable of correcting for that degree of mistakes. However, for signaling, we only send it across 4 bursts. And for circuit switch data, which is fairly uncommon today, we would actually spread it across 22 bursts. The benefit here is that if we lose a burst now, we'll be losing an even smaller sample from one 456-bit block of information. So, in summary, what have we seen in this high-level overview of our protocols operating across the GSM air interface? Well, as far as our first protocol, DTAP, Direct Transfer Application Part, we could see this was really a combination of specific signaling messages running between the mobile and the core network, or our MSC server. In addition, we also have radio resource, which again carried either common or dedicated signalling, but this was really associated with establishing the connections and maintaining the connections just across the GSM air interface, again dealing with radio resource. Both of these use the services of LAPDM, the link access protocol on the DM channel, which not only allowed us to differentiate between our signaling and our SMS, but also enabled us to run in acknowledge mode, the ability to call for retransmissions if some of that information was errored. And finally, we saw the process of channel coding and interleaving for both the enhanced full rate and the AMR codec. Again, applying different degrees of convolutional encoding, but resulting in a channel rate of 22.8 kilobits per second. These then could be spread across different degrees of bursts. 8 for speech, 4 for signalling, and, should we come across circuit switch data, 22.
Need to know more? Why not visit our store, where you can choose from over 200 hours of video-based training. Alternatively, you can contact us to discuss any specific training requirements you may have.